In this video, we're going to go ahead and cover section 9.4, Mathematical Induction, part of Unit 9, Sequences, Series, and Probability. A lot of the examples are worked out for us just because this is a kind of lengthy section. But just to kind of give a little bit of background information, this is the tip of the iceberg when it comes to proofs. Pretty exciting stuff if you're into math. We're going to just kind of do the basics in this one. It's kind of a shame we don't go too much into induction, but hopefully you get the concept. Okay, so here we go. We have the principle of mathematical induction. We're going to let P of n be a statement involving the positive integer n, meaning, and I kind of want to put this here, n would be a positive integer. This is another notation for saying that n is an element or belongs to the set of integers, and we put this little plus here that means it's the positive integers. Okay, just kind of a side note there. If P of 1 is true, so in other words, if the first case is true, where you plug in a 1 into whatever the formula is or equation or expression, if that's true, and for every positive integer k, the truth of P of k implies the truth of the following, then that means that it must be true. So let me kind of explain what that means. Case number 1 is true, and what happens is we assume that the general case is true. We're saying, well, if this is true, well, then this must be true also. But if this is true, if we assume that this is true, well, then we have to prove that the following term is true. So we do this k plus 1. You're basically adding another term to the original um, expression or whatever we're trying to prove. And if this one comes out okay, well, then that means that the whole thing is true. Kind of cool. It goes a little bit back to, I want to say, if A equals B, then B equals C. I'm sorry, if A equals B and P equals C, then A equals C. Kind of one of those concepts. I want to say it was Aristotle or so. But anyway, let's go ahead and start an example. This first one's worked out for us just to kind of identify what it means to do P of k plus 1. So we have this statement here. It says find the statement P of k plus 1 for each given statement P of k. So what you're given here is you're given the original expression. I guess I can kind of move this over, cover this part here with my little device here that doesn't even work. All right, so these are the three statements, the three pieces of case. So we have, and I noticed that I did use S of k for this one. It just kind of depends on the problem, but basically the expression is this right here. So 6 over k times k plus 3, that's the first one, and then this one is k plus 2 is less than or equal to this. This one is 2 to the power of all of this plus 1 is greater than 5k. So you just have these general expressions, and we're just going to identify how would you find p of k plus 1. Okay, well, all that you really do is you take k plus 1 and you plug it into the k, and that's basically it. So here's the first one. You'll notice that all I did is I took my k, I'm trying to find my blue pen here. I took my, where I have my k, and I put in a k plus 1. So you're kind of substituting. Yeah, that's it. This goes where that went. And then this k is also replaced by k plus 1. You simplify if you can. We'll notice that 1 plus 3 equals 4. So this is the equivalent to our piece of k plus 1. Okay, real basic stuff. Look at the next one. So you have a little bit more complicated stuff going on here because you have a square and you have some other stuff. So you'll notice that same deal, we have our k. So I just basically plugged in a k plus 1. Sorry about that. I'm out of whiteout, so we're just going to scribble now. So k plus 1 right here. We have another k over here, so you'll notice that for that k, I also substituted k plus 1. Okay, and same deal. You simplify if you can. So this one, I can add 1 and 2, which is 3. For this one, we have a 1 and a minus 1, which is going to give us a 0, so we just have a k. And you could technically leave it like this, but we want to make it look a little nicer. So k plus 3 is equal to 3k squared, and this again would be our equivalent to what is represented for p of k plus 1. Okay. Last but not least, we have this one right here, and this one has a power, and it has plus 1 greater than or equal, I'm sorry, greater than 5k. So you'll notice that where my k is, again, I replaced it with k plus 1. I kind of had to squish it here because there was not much room, but this is replaced by this, and then this k is replaced by k plus 1. So simplify, and we get this. Okay, so The reason we need to go over this is because for the actual proof of induction, we do have to be able to write this out because this is where we kind of work with numbers, okay? So there we go. That's the first example. Let's go ahead and try an actual proof now. So let's look at the next example, and it's going to be example number 2. It says use mathematical induction to prove the formula, and then we have this kind of like a sum going on here, right? 5 plus 7 plus 9, etc. Plus 2n plus 3 is equal to the following. For all integers, n greater than or equal to 1. And notice I do have the notation here. This notation, I have not mentioned it too often, but this right here means for all. So this is what you would see like in an actual college class on, UTEP or wherever you plan to go. They're gonna, instead of writing for all, they would put this upside down A looking thing. But it means for all in whatever number we're doing, in this case integers, such that they're greater than or equal to 1. Okay, so let's go ahead and try this. We're going to go ahead and follow the rules that were listed kind of on this page right here. Okay, so first thing to do, step number 1, is to show that P of 1 is true. And this is basically your base case. It's the first case. What we're going to do is we're going to look at our first term. So our first term is supposed to be equal to 1, right? So S of 1 should equal, I'm sorry, not 1, 5. S of 1 should equal to 5. So we're going to say if this is 5, if I plug in a 1 into this right here, it should come out to 5. So we're going to check. Let's see. N times n plus 4. If I plug in a 1, I get 1 times 1 plus 4, which is 1 times 5, which is 5. So it looks like our base case is true. So this first condition is met. And that's how you always start these. You see if it's going to work for number 1. And it does kind of depend on the problem. Sometimes if it tells you greater than or equal to 2, for instance, then your base case would be 2. It just depends on what you're starting with here. Most of the times it is 1 though. Okay. Let's look at the second step now. So this is where it gets a little tricky because we have to assume that P of k is true. Now, what is P of k? So P of k is basically this up here. You just replace n with a k. That's it. It's just some arbitrary integer k that we don't really know what it's equal to, but it's just, some number. So we're going to say assume that P of k, which would be, in this case, S of k, because it is defined with, a different notation up here, which is equal to 5 plus 7 plus 9 plus 11, all the way to, let's see, dot, 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 plus 2k plus 3. So all we're doing is replacing all the n's with k's, okay? And that is supposedly equal to k times k plus 4. So we're going to assume that this is true, okay? And if this is true, we have to prove or show that P of k plus 1 is also true, which in this case would be, since we have our notation with s here, I'm just going to put s of k plus 1 is equal to, I'm going to probably have to write this on the bottom line, but basically this is going to be all of this and then one more, yeah? So you're thinking 5 plus 7 plus 9 plus 11 plus dot, dot, dot. We just copy it, plus 2k plus 3. So this is the original, okay, this whole part right here. Plus, we're going to add another one. So kind of like we did P of k plus 1 on the other side, we're going to replace this k right here with the k plus 1. So we have 2 times k plus 1 plus 3. And this is all supposedly going to equal to this, which again, we have to replace with k plus 1. Takes some getting used to. Okay, so just so you can kind of see what I did replace, I basically copied all of this, right? So all of that is right here. So you just kind of copy it because k plus 1 is basically the original and then one more, yeah? So, and then I replaced this k with k plus 1. So there's this k plus 1 term right here. Same thing where it's equal to, so I replaced these k's with k plus 1. And this, for some people, is the hardest step, just being able to set it up, okay? Because now we're going to prove it, and this is where it gets a little fun. Well, fun for me anyway. We know that this whole thing right here, and let me see if I can turn this a little bit. This whole thing right here is the same as, well, S of k or P of k, right? I'm going to put S of k. Don't worry too much about the notation. Basically, this is the same as this, what I underlined, okay? So that means that I can replace, so we can, or substitute if you prefer, we can replace with what this is equal to. So up here, we assume that this is true, which means that we can replace all of this with just this. So that's what I'm going to do with k times k plus 4. Okay, so here's how it's going to work. We're going to have s of k plus 1 is basically s of k plus the extra stuff, okay? So how do I do that? Well, yeah, we can do it that way. So it's basically this plus all of this. So 2 times k plus 1 plus 3. Okay, so again, this right here represents s of k because s of k was here. So this equals that. So these two are the same. So I'm replacing all of this with s of k. Okay, so I'm going step by step here. So that's going to be equal to k times k plus 4, okay, plus, again, this whole thing here, 2 times k plus 1 plus 3. So one more time. This is equal to this is equal to this. These three things are equal. In my expression for p of k plus 1, I have that whole thing. So this whole thing, I'm going to replace it with that, basically, which is what I did right here, okay? And then from here, we just manipulate. We manipulate this to match what I want it to match. So manipulate to match. I'm going to put star because I don't want to have too many arrows, but this right here would be star. Basically this part right here. Okay, so let's do that. This just becomes, k squared plus 4k. I'm just distributing. Plus, I'm going to go ahead and leave this in parentheses for now. So let's distribute. We have 2k plus 2 plus 3. And then that's going to give us k squared plus 4k plus 2k plus 5. We're almost done. This is the same as k squared plus 6k plus 5. You'll notice that we can factor this right here. So I'm going to do that. K plus, I believe, 5, and then k plus 1. Okay, and we're kind of done. You'll notice up here that these are not exactly the same, but, and this is kind of optional for you. You can either change it here, you can change it here. Here, this is the same as, well, k plus 1, and then 1 plus 4 is 5. So we are good to go. We have just proved it. And if you didn't want to go that route, you could also just kind of change this one to match because k plus 5 is the same as k plus 1 plus 4, yeah, which is right there. So we have proven using mathematical induction that this is true. So here's how you end the proof. You say, so by 1 and 2, because that's what we kind of did. 1 was the base case, 2 was the assumption, and then checking the proof here. So by 1 and 2, by mathematical induction, we probably should start with that. By mathematical induction, this is basically true. So we can say that, what was it again? S of n equals n times n plus 4 for all integers, positive integers. We'll do it like that. And this concludes the proof. Pretty cool. Takes some getting used to, okay? Let's look at another example, and I think this one I kind of started it off for us just because of the time, and then we have to finish the end. So this one says, use mathematical induction to prove the formula. Let's kind of cover this for a little bit. S of n is equal to 1 times 1 minus 1 plus 2 times 2 minus 1 plus 3 times 3 minus 1, and so forth. Oh, I forgot to put the dots here. Dot, 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 plus. Okay, so it goes on, right? And this is equal to the following formula. So we're trying to prove that this is equal to that, okay? For all integers, n greater than or equal to 1, and again, here's that notation. You can do it like that. You can also just kind of put the little plus right there so you don't have to write that down. So let's look. The first step is to show or to check the first case. So you can see here that for P1, which would be our very first term, so this term right here, this is our P1, would be our 1 times 1 minus 1. So that's just 0, right? 1 minus 1 is 0, 0 times 1 is 0. So it's supposed to come out to 0. So if we plug in our 1 into the formula, we get 1 times 1 minus 1 times 1 plus 1 over 3. And just right here, I mean, you see that that's equal to 0. So anything times 0 is going to give us 0. So we are good to go for the first step. Okay. Step number 2, and this, I tried to make it as neat as possible here. It says assume P of k, which is our, I guess, kind of a sum up here, right, is true. So basically, I just recopied it. This is the exact same thing that's up here, but instead of n's, I used k's because we're using an arbitrary integer k. So assume that that's true. If that's true, then we need to show the following. Okay, and here I kind of tried to color code a little bit here so you can see what replaced what. So just real carefully, we have s of k, and this is s of k plus 1. So you'll notice that this entire piece right here, okay, so this whole piece right here is the same as this piece right here. So I'm just replacing, s of k with this. And we have to add one more. So one more would mean we would take our k's and put k plus 1 there. So k plus 1, k plus 1 minus 1. I just replaced k plus 1 into these two spots right here, okay? Same thing with these. We replace k plus 1 here, here, and here. So you'll notice that we have our, I guess I can go over it real quick. This is k plus 1 in this part. This is k plus 1 in this part. And this is k plus 1 in the third part, all divided by 3. So we're going to try to prove that it comes out to this. And I think for this one, yeah, see, for this one, I went ahead and simplified it because that's a lot of parentheses. And I just think it's a little easier to work with less parentheses. So we simplified it to this just to make it easier for us. Okay, so let's see how we did that. We remember, ignore that. Again, I'm out of whiteout, sorry. We remember that from the previous example that s of k plus 1 is basically just s of k plus the extra term. So kind of like what I did in the first one. So I basically just copied whatever s of k was equal to. So remember, s of k was what I had up here. So s of k, where is it here, is equal to this. You want to copy the formula part. Okay, this is cool, but we want the formula part. So this gets replaced with s of k. Okay, so there it is, and there it is. And then we just recopy this part right here next to it, okay? Now this one requires some manipulation because when we're trying to combine this one has a fraction, this one does not. So we're gonna have to find a common denominator for this. So basically what I did is I just multiplied times 3 over 3, which you're allowed to do, it's just a 1. And that's gonna give us the following, okay? So you'll notice well, actually before I did that, I went ahead and, what did I do here? Oh, I simplified this part. So 1 minus 1 is just 0, right? So I did that preliminary step. And then here's where I did the times 3. So you have the original plus 3k, so 3 times basically all of this right here, all over 3. Now that we have division by over the same denominator, I'm sorry, we can go ahead and work this out. So that's what I did next. Did I finish? Oh, I didn't finish it. So we're going to finish it together, okay? So let's see. We have for this part right here, so for this part right here, actually, no, let's do it. This makes this easier. You'll notice that we have a k in both spots. So we're thinking kind of like this and like this. Okay, we have a k, so I can actually factor out a k. I also have a k plus 1 in both little sections here, so I'm going to factor that out as well. And if we do that, we're basically left with two things inside. Well, in this first one, since I took out k and k plus 1, I'm left with k minus 1. And in this one, I took out k and k plus 1, so I'm left with 3. So we're left with that all over 3. We can simplify. So k times k plus 1, negative 1 plus 3 is k plus 2. And I think, ladies and gentlemen, that that is what we were looking for, because if you look up here, that's what I have. Yeah, they're in a different order, but it's fine. It's multiplication. You can rearrange it. Yeah. So, if you want to put in parentheses, it's fine. But we have proved it. So again, we can say by mathematical induction, something along these lines, 1 and 2 prove that S of n is equal to n times n minus 1 times n plus 1 over 3. And I'm just copying this from the top for all integers, positive integers. Okay, and that is it for that one. All right, moving on. We're hoping the video is not too long, because induction does take a little bit of getting used to, and it's kind of lengthy, as you can see. So the next one I actually solved for us as well. It's not too bad. So I figured, we could just follow along. We're going to prove that n factorial is greater than or equal to n for all integers that are positive. So n factorial, remember, that's the one where you multiply. If it's like 5 factorial, you go 5 times 4 times 3 times 2, and you just kind of go backwards. So here's a solution. Base case, okay? We check 1, because that's the first number we start with. So 1 factorial greater than or equal to 1. Well, 1 factorial is just 1, and 1 is greater than or equal to 1. So we're good. True. 2, assume that P of k is true. So in other words, just plug in a k and say that's true. We're going to show that P of k plus 1 is true. Okay, so basically what I did is I said, well, wherever I have a k, I'm going to put a k plus 1. So there's k plus 1 there, and there's k plus 1 there. We're going to have to prove that. I did put a side note here because I don't know if you guys remember this or not, but you have to remember that if we have k plus 1 factorial, and you're going backwards, it's kind of like saying k plus 1 minus 1 times k plus 1. So this is a quick note there, that k plus 1 is factorial is equal to k times k plus 1. Okay, if you don't understand this part, let me know in class and I can kind of show you some more examples with that. But we need that, okay? It's because what happens is, well, when I write out my formula here, I do this, right? This is equal to that. You'll notice that this, since I said it's equal to, I told you it's equal to this, well, this is just equal to this, right? K plus 1 factorial is k times k plus 1. And you can tell just by looking at this that this is true, because since our integers are all positive, well, you have the same thing on both sides, k plus 1, k plus 1. And then you have another number being multiplied. So that means that this side's going to have to be bigger than this side, or at least equal to it. So that kind of just proves it right there. So by mathematical induction from 1 and 2, our expression is true. Okay, pretty cool. Let's look at the next example. We have 7 examples total. Okay, so we're trying to get through this relatively quickly. Prove that 2 is a factor of 3 to the power of n plus 1 for all positive integers. This is a cool one because you have to do kind of a different method. So let's start right away. We're going to find, so for 1, we're going to do P1. So for P1, basically I'm going to plug in a 1 into my n. So 3 to the first power plus 1, that's 3 plus 1 is equal to 4. And 4 is divisible by 2. Okay, 4 is divisible by 2, which is what this is saying. 2 is a factor. So yeah, by the way, another way to write this, if you want to think college terms, you write like this. 4 is divisible by 2. Okay, so check. Check for the first one. Second step, here's where the induction part comes in. We're going to assume P of k is true. So in other words, we would have 3 to the k plus 1 is divisible by 2. Okay, or if you want to be fancy, you can do it this way. Some college stuff for you there. And we're going to show that p of k plus 1, which would be equal to, let me see, we're going to take our k plus 1 and just plug it in, right? So 3 to the power of k plus 1, yeah, excuse me, is also, we have to show that that is true, okay? So show that this is divisible by 2. That's what we're trying to prove, okay? If we can prove that it's divisible by 2, that means that 2 is a factor. So that's why I keep writing that word divisible by 2. So let's work this out. See how we're going to do this. Like I said, this is kind of a neat one because you got to use a little bit of little bit more tricks here. So we're going to do 3 to the k plus 1 plus 1. You got to go back to your rules of exponents here. So I remember that when you're adding like this, you can rewrite this as multiplication with same bases, like 3 to the k power times 3 to the first power, and then the plus 1, right? So we know that if you were to like combine these, like basically I expanded the exponent. But if you were to condense this, it would go back to this. You just add the exponents. Okay, so that's what I did here. And then here's the extra trick. We're going to actually add and subtract something to this to make this work, because so far this doesn't really, I can't really do much with this. It's just kind of there. So here is this extra cool step. We're going to rewrite this, and I'm actually going to subtract 3 to the k and add 3 to the k, which I'm allowed to do because this is just equal to 0, right? A negative and a positive with the same exact thing is just equal to 0. So I can do this. But why am I doing this? Well, because if I do this, you'll notice that we can kind of sort of group them a little bit easier. So these two terms right here now, oh, I'm sorry, not that term. This is what I meant. My bad. Ignore that. Those two terms right here, if you're going to just kind of factor that, they both have a 3 to the k, right? So you can do this. Pull that 3 to the k out, and you're left with 3 to the first power minus 1. So all I did is I basically divided out 3 to the k from this term. So here, let me kind of circle it from this term and this term. These ones I'm just going to write them down. So plus 3 to the k plus 1. Okay. So there's that. And check this out. So you will notice that, let's see, where's my assumption? That this part right here is exactly what I had up here. So this part is P of K. So by our assumption, we're good to go there, yeah? So all we really have to work out is this part right here. So let's kind of fix that. We can do is equal to 3 to the k. 3 to the first power is just 3. And then we'll just kind of put that there. We'll pretend it's there. Keep going. So 3 to the k, and then 3 minus 1 is equal to 2. Let me rewrite this now. And I mean, we know that 2 is divisible by 2, right? 2 is a factor of itself. So from here, this is p of k, so that part's good to go. And from here, we have it as divisible by 2, because again, you have a 2 there, so therefore it must be divisible by 2. So we are good to go. And we're going to just kind of end the proof there. So by mathematical induction, or thus by mathematical induction, whatever you want to start with. Okay, induction from 1 and 2. Okay, what is our expression again? 2 is a factor of 3 to the power of n plus 1 for all positive integers. And you'll find as you continue your mathematical education, hopefully some of you, that a lot of the proofs do use little tricks like this. And as you do more of them, you'll get better at them, okay? Like I said, tip of the iceberg, tip of the iceberg. So here is example 6. I don't know how long we've been going so far, but hopefully it's not too long. This is finding a pattern using, I'm sorry, it's finding the nth term of a sequence using pattern recognition. So here's a few steps. You're going to basically calculate the first three terms, simplify, factor if you can, and then look for the patterns. Yeah. Write a formula, which we also call our conjecture or the hypothesis, and then use mathematical induction to prove it, which is the main focus of this one. So here we go. I did some of the setup just so we can kind of go through it. Just find the formula for the finite sum and prove its validity. I can never say that. So here is the sum: 3 plus 7 plus 11 plus 15 plus etc. plus 4 and minus 1. Okay, so we need to find what that's equal to. Usually it's equal to some kind of expression, right? So what I did here is I calculated each of the sums. So for example, the first sum would just be the first term, so it's just a 3. The second one would be the two terms, so 3 plus 7 is 10. The third one is, well, the three terms, which gives us 21, and the fourth one is 36. You add all four. And of course, it keeps going, right? So what we're going to do is what we did kind of in the first part, I think it was 9.1, we were trying to figure out a formula to get these numbers. Okay, remember that this is equal to S of 1, this is S of 2, this is S of 3, this is S of 4. So whatever you decide your values to be here, you have to multiply by K. You're thinking of these numbers right here, okay? I am going to use a pencil for this part because I might have to erase some things, yeah? So let's see. I know for 3, if I have to use a 1 in there somehow, well, I know that, let's see, 2 times 1 plus 1 would give me 3. So maybe we could use that. So let's see if that would work for the second one. Let's see, we have to use a 2. So if I do 2 times 2 plus 1, let's see, 2 times 2 is 4. Oh, that's not going to work. That's 4 plus 1. But I know that this one is 5, right? So what if I multiplied all this by 2? That might work. So maybe. Let's see how we can remember this right here is our K. So think about where the K is. Okay. Maybe that could work. Let's see if we're gonna use, and this, let's say we make this K also, because it's not gonna, if we look at it, the first one, if I multiply this one by 2, it's gonna change the value. So if you multiply it by K, okay, put this kind of like in parentheses. Okay, don't, it's not a power. I'm just showing you where it's located. If I multiply this by our K value, then we would get 3. So this works so far. So let's try it for the next one. Let's see, we have 2 times 3. Remember, this is K plus 1. 2 times 3 is 6 plus 1 is 7. And I know that 7 times 3, which is our K, would give me 21. So it looks like this is the pattern. So let's see. The next one would be 4 times 2 times 4 plus 1. So 2 times 4 is 8, plus 1 is 9, times 4 is 36. Super cool. So that means that my formula for this is basically going to be, let me see, I have a K in the first spot. So K, and then we have a 2 in the second spot, and another K plus 1. So something like that. Let's write it a little more officially. It would be K times 2K plus 1. And this is what I'm going to go with. I think this is the formula we're going to have to use. Okay, so far we found the formula for the finite sum. We're going to go ahead and prove it using induction, which I actually kind of started on the next page. Okay, so let's go ahead and do that. And you'll notice it's already proven for us. Wow, isn't that magical? So here's the example 6 continued. And I'm just going to go through it real quickly. We do have one more example after this. I promise the last one is pretty simple. Using what we had on the page before, you're going to prove the first case. So base case is P of 1. So plug in a 1 into wherever you have a case. So 1 times 2 times 1 plus 1. You work it out, and we do get 3. So awesome. Second part, we're going to assume that P of K is true, which means that the following is true. Basically, our sum here, so I just recopied it all the way to 4K minus 1. Remember, you put the K where the N is equal to our formula. So K times 2K plus 1. We're going to use that to show that K plus 1 of, the subscript is true. So basically, I copied all of this part from here. It's the same thing, and I just added one more. So plus 4K plus 1 minus 1. So this part right here is basically this part, but instead of your K, you have to put that K plus 1. Okay, and that's equal to, well, this guy, but with K plus 1. So I just took my K plus 1s, put them here, And then I simplified this because that looks, oh, actually, I didn't simplify it. So let's do that real quick. So this is all this. So what I'm going to do here is I'm going to simplify that because it's a lot of parentheses. So this would be k plus 1. 2 times k plus 1 would be 2k plus 2. We still have the 1 there. So you're thinking k plus 1 times 2k plus 3. So this is what we're going to try to make it equal to. Okay, so let's see. Let's see what we did. So we know that s of k plus 1 is basically all of this plus 1 more. So I just copied s of k, which is this guy. Okay, so there is that part right there. And then the new part, so plus 4 plus k plus 1 minus 1. And then from here we just manipulate. So this part that's the same. I distributed, so 4 times k plus 1 is 4k plus 4. There's the minus 1. Combine like terms, so we have a 3 here. Let's see what else. We foiled, so I would not foil, distribute. We did this. So that's 2k squared plus k. And I brought this down. Combine like terms, which is 2k squared plus 5k plus 3. Factor, and lo and behold, we are correct. So we got the right formula, yay us. And that means that by mathematical induction, our conjecture is valid for this sum. Okay? Yay. Oh, let's make that nicer. Yay. Still kind of creepy looking, but you get the idea. Okay? All right, let's look at the last example. We're going to go kind of fast here. Actually, you know what? I think I'm going to stop. Go ahead and copy this. We will go over this in class very quickly because I'm pretty sure we're a little bit over on time. So copy this real quickly, and there's a few seconds. And then here are the last two problems. These are the easiest ones in the whole video, so I'm not too worried about them. As always, if you have any questions, let me know. This is kind of a difficult concept, so, for sure, reach out if you need to.